Hello, welcome to Security Cryptography Whatever. I'm Deirdre.
I'm not David Adrian.
Thanks. That's Thomas. And we have a special guest today. We have Jeff Vander Stoep, who is from the Android team. Hi, Jeff.
Hey, everyone.
Hi.
He sounds really excited to be here.
He is doing us a big favor by joining us late at night his time. We invited Jeff on because he helped co-write a blog post from the Google security blog recently entitled Eliminating Memory Safety Vulnerabilities at the Source. And to TLDR it had some very interesting results from deploying and adopting Rust in practice in the Android project, and how basically walling off your old memory unsafe code with a nice abstraction boundary and only writing new code in memory safe languages like Rust and others significantly reduces your vulnerabilities over time in a sort of non-obvious way, which does not involve rewriting the world in Rust or rewriting the world in Kotlin. And so we just wanted to ask him a whole bunch of questions about this.
Jeff, real quick, you guys are still writing some C++ code or whatever. Like if you look at the graphs and stuff, that's one of the counterintuitive things about the results here is that despite the increase in memory unsafe code, you're seeing a metric decrease, like a sharp decrease in memory safety bugs. But that was a reasonable summary of what you're up to?
Yeah, I think so. As far as what code we're still writing, yes, we are still writing and touching some C and C++ code. And, we expect that to continue to happen over time, but also to decrease over time.
Okay. That was not obvious to me when I first went through this. What memory unsafe parts of your code base are you adding to, and how are you restricting that over time to align with sort of this new perspective on how you approach adding to your code base over time to mitigate and minimize vulnerabilities?
Yeah, so we have kind of recommendations and best practices for things that teams should be doing, but also we're not trying to be over pedantic on things or put too many restrictions in place in order for teams to be productive. Instead, what I would say is that we are encouraging and incentivizing teams to use memory safe languages. And of course, as more and more teams switch, the bar and the impedance to switching goes down over time, right? Mm-hmm. And so instead of trying to put in a bunch of rules and restrictions in place, instead, teams are kind of switching naturally, right? And nice. as more code is in Rust or in Java or Kotlin or whatever, then that actually encourages the same.
So can I get a better sense of the threat model here? So I have an intuition for what the browser threat model is, right? What you're, and also a sort of sense of what code is getting written there and what the security hotspot code is there and all that, right? And I feel like I don't have as good of a sense of where new code is written, what kinds of places in the Android code base tend to be implicated in vulnerabilities, that kind of. So as a starting point, what does that footprint look like? Your starting point for this was, what was that?
Yeah, so we actually talk about this a little bit in the blog post, but one of the challenges that you have in running an operating system is that the threat model is really, really complex. Mm-hmm. So we have things network interfaces, which kind of similar to a browser are an obvious entry point, right? But also we have to be able to run untrusted code. Mm-hmm. Users can install a third-party app, for example. And so we have everything from image parsers, network stacks, even network stacks and firmware, for example. But then on top of that, we have other APIs that are then reachable to third-party apps. So one escalation path that we could see is you exploit a messaging app with a malicious image file. And then from the message app, you then exploit the GPU kernel driver. And then once you're in the kernel, then you basically have access to anything that you want on the device, right? And so what's kind of interesting from our standpoint is that trying to decide which of those things you spend effort on is itself a pretty large cost.
Yeah.
And so part of what we want to do is actually spend less time doing that and just be able to say, now everyone can do things that are safe, and we can just eliminate a threat and not have to worry about a threat. And that's part of what we're seeing, right? So we now have different pieces of code where we just don't have this problem anymore. And it's really nice. We just don't worry about it in those areas anymore.
So if I'm following that, and if I'm trying to like make a I hear you saying that one of the things one of the benefits you're hoping to get from, ramping up the use of Rust code on the Android platform is to not have to have intricate models of like where the sensitive code is and where the, where you could tolerate memory corruption versus where you can't tolerate memory corruption, that kind of thing. You just take it off the table is the idea, right? But like, as I'm listening to you, it's occurring to me that like, so if I think of what Android is, like my first thought is, okay, it's the kernel, which is really hard to get Rust into. And then I would have thought like, system applications and things like that you're shipping. And it's occurring to me, this is also a lot of framework libraries. That isn't the operating system itself. It's code that's getting pulled into every application that gets shipped on Android, right? But like, am I right that some of the code that we're talking about here is just like, for instance, like an image parser library, like I don't intuitively see that as part of the operating system unless there's a system app that uses it. But you're saying like, am I right that like that Android applications that other people write are using that code as well? So we're also thinking basically about like what the libc is and what the image parser is and like your libpng or whatever that is, right? That stuff.
Yes. Yeah, exactly. And to give you like broader context, for example, we have, maybe 100 different HALs that are running on a device. We have all of the system APIs, anything that requires a permission check has to be done across a security boundary. Mm-hmm. So that's another process that API is running in. And so I wish I had ADB access on my device right now. Like I, could do a PS and you could see that like there's, 1,000 different processes running right now on my device, only a small subset of which are actually applications.
Mm-hmm.
Yeah, I mean, one of the things that's occurring to me is I'm wondering if there is a knock-on effect of the operating system work that you're doing, of the Android work that you're doing, that is also, like, it's interesting to think that if you kind of took this to its logical conclusion, you could be swapping out a fair bit of application code for your developers, right? Without them having to think about it being memory safe, keeping the same interfaces, but they're still calling into it. And now like parts of their application are written without them having to think about it in Rust as well.
Yeah. And Java and Kotlin. And what I would say is that when you install an application on your device, probably in most applications, most of the code that is running actually comes from the operating system and not actually what was shipped by the developer. Of course, there are large exceptions to this, like browsers being an obvious example.
So when you're talking about the security boundary, we already, in like an OS or even in a browser, you already have notions of a security boundary that are kind of like baked in, where you're like, oh, all of this stuff is over here. This is trusted. This is like in the kernel or, far away. And this other area over here, like this is definitely where this is attacker controlled supplied data. This is untrusted. And you have to do something between one to the other or vice versa. How does that change, if at all, when you are starting to rewrite parts of these things in a language like Rust that just mitigates a whole class of vulnerabilities that used to kind of be encapsulated as, that stuff is behind that security boundary? Like, do you have to evolve the notion or existing notions of a security boundary in this sort of world?
Yeah, so memory and safety is kind of a unique example for vulnerabilities because they lend themselves to being chained together.
Yeah.
And so when you have high-risk code, what we often do is we often isolate high-risk code by itself. Mm-hmm. And so as the risk of code changes, we will be making and already are making different decisions.
Okay.
Based on what level of isolation that we provide to different things. So if I can replace a memory unsafe parser with a memory safe parser, then I'm probably not going to sandbox that, regardless of whether or not it processes untrusted content.
Okay. And do you have any other sort of, I want to say like a rubric or a way of scoring, like whatever, scoring, evaluating, whatever you want to call it? Like we kind of have like a instinctual feeling that like if I have a parser implemented in Rust with no unsafe keywords or anything like that, or any weird exceptions under the hood, I have a pretty good feeling that this is a much safer parser and much less likely to have a, a high, a critical vuln versus one that's written in an unsafe language. Therefore, I feel pretty good about not putting that in a sandbox. But do you have any other kind of ways of evaluating, like, okay, the security boundary that I need for this component is different than this other component, other than sort of like, yeah, seems all right?
Yeah, I mean, memory unsafety doesn't or memory safety doesn't replace good security architecture, right? So we still split things up into logical groups, and this isn't just a security thing, right? This is like basic like system stability and reliability and other things that we want.
Yeah.
So yeah, like we're still going to split things up into logical components. We're still going to do things like principle of least privilege.
Yeah.
For various sandboxes. Yeah. Does that answer your question?
Yeah, to a degree, which is basically like you kind of have to see each component for what, or each module, as it were, for what it is. Because like if it's a memory safe parser, but the worst thing that component can do after you've parsed some attacker controlled blob is like read, that's different than if you like have a parser that's written in Rust and it parses the thing, and the thing that it can do is read and write and do an inter-process who's-y what's-it. Like the capability makes a difference there too.
Yeah, and what I would say for parsers is that for parsers in general, I wouldn't even say in general, the vulnerabilities that we have in parsers are memory safety vulnerabilities. like we're not having permission check vulnerabilities, right? Whereas like you could have that in like a network stack if it's screwing up a permission check or a encryption, or there's lots of stuff that can go wrong in a network stack. But for like image parsers or any other type of format parser, like the vulnerabilities are memory safety vulnerabilities.
Cool.
I'm looking at the blog post. we're gonna, as usual, we're just gonna like take a shotgun blast of this whole thing, right? So there's an interesting graph early on in the post. Like you have like a kind of a simulated model of ramping up memory safe code versus memory unsafe code, and then you have the actual empirical data from lines of code from the Android open source project, right? So I'm looking at a graph starting in 2019 where you're about like a third memory safe versus memory unsafe code. And then in 2024, it's now like roughly half and half, maybe a little bit more, like maybe closer to, so maybe that's like 60% memory safe. There's no numbers in the graph, but that's roughly what I'm looking at, right? So I have a couple questions, right? So first of all, 2019 feels early when we talk about memory safety, like with people in the zeitgeist about memory safety, right? That's Rust. Right, that's code for Rust, right? It's like when I know it's not in your case. I but like in the zeitgeist, when people hear memory safety, they're thinking, oh, we're talking about rewriting things in Rust. But in 2019, that couldn't have been. Like you could not have been a third Rust code, right? So what does memory safe code there mean in 2019? Is that Java and Kotlin?
Java, just Java.
Okay. And then it looks like you've roughly doubled the amount of memory safe code from 2019 to 2024. Like the ratio has changed, but also if you look at the chart, it's like, it looks like the amount of memory safe code in the Android open source project is about double. Like how much of that is the initiative to start doing like, how much of that is stuff that wouldn't have been memory safe before? And how much of that is, this is Java/Kotlin code and we just wrote more of it because that was part of the same project?
So I think there's some of both, right? Like we actually do have things in place to encourage teams to shift. So like one of the things that we talked about in a previous blog post was that even in the past, we would use the rule of two in order to encourage teams. God, how do I describe the rule of two? It's essentially that, like, if you're going to process untrusted content in a memory unsafe language, then you have to sandbox it. If you use a memory safe language, you don't have to sandbox it. And so even a few years ago, we kind of had things in place that would actually encourage teams to use memory safe languages. And so, yeah, just, imagine things like that, and how that encourages what teams do. Like, today we have examples where, like, no, I actually need native code to process something. In the past, what they would have done is they would have used C++, for example, and then we would have forced them to sandbox it. If a team has that decision now, they're going to use Rust because the sandbox penalty is a penalty they would like to avoid.
So the rule of two, it sounds like something that's broader than sandboxing. It's like
they also have it in Chromium, but yeah.
But the implication
it actually came
is
from Chromium.
Okay, so I guess one question I have is, you also have a graph, and we'll come back to it, of the sharply declining number of memory safety vulnerabilities over time, right? If I'm thinking about where you guys were at in 2019, just to try and get a sense of what this whole trend looks like, right? Were you guys like 100%? 100% is a weird way to put it, right? But like, were you broadly, kind of generally, categorically applying that? Like, if you're writing memory safe, was all the memory safe unsafe code sandboxed in 2019, or did that also increase from 2019? As you ticked forward from 2019 to 2020, did you also increase the number of sandboxes and stuff you had as you caught more, or were you at that point already caught up on sandboxing? You were already doing that?
Yeah. So one of the things we talked about is how we're actually, so we have written about this, and Chrome has written about this as well, which is that sandboxing has limits. And it has like system resource limits. And so quite often we couldn't necessarily make security decisions that we would have wanted to, because the penalty for it was too high.
Yep.
And so that's another thing nice now, right? Is that we don't have to make security versus like performance trade-offs. We can just do both.
That makes perfect sense, right? I'm trying to develop an intuition for what it looked like when you guys were sandboxing something, right? Are we talking about, like, is the sandboxing overhead there like IPC overhead, like we're running multiple processes, or was it like, we're doing, we're instrumenting code as it runs? What was it? What is like the archetypical, somebody wrote a big memory unsafe blob of stuff and we have to sandbox it? Like, what do you think the default is there?
Yeah, so the media frameworks, Android's media frameworks is actually the perfect example of this. So before the stage fright vulnerabilities in whenever that was, 2015, we had one massive media server process, and it had, all of the camera stuff, all of the codecs, all of the image processing, like it had access to all of the kernel drivers that it needed to for hardware. It had all of the HALs running in process.
Oh boy.
And I think that single media server process now is something like 14 separate processes in Android now, where we've actually not just like split out the risky parser code into like very kind of deep, like unprivileged sandboxes, but we've also just kind of logically split up, like the audio processing now all takes place in two processes, actually something called audio server and then an audio HAL. Similarly, like the camera is the camera server and the camera HAL. And so it's, on the one hand, like everything is kind of like split out better, but also like we can't keep doing that for forever, right? Like we can't take every single process and split it out into 14 processes.
Okay.
Like we just don't have the budget for that.
So when I'm thinking about sandboxing here, like the right way to think about it is roughly the same way that, Chrome is divided up into, at this point, like microservices. And all the attendant overhead. That makes sense.
Okay. I'm going to switch over a little bit, because this is sort of like, we can take code that happens to be written in a memory unsafe language and restructure it wisely. And once upon a time, it used to be, if it's in a memory unsafe language, you must sandbox it. If it's in a memory safe language, you don't have to sandbox it. Like you have to pick one. And One of the interesting things that came out of your post that seemed counterintuitive was that the old memory unsafe code, importantly, matures and gets safer with time exponentially. Not just that, like, you know, it will stay steady state. It will get safer with time with an exponential decay. And then if you're only writing new code in a memory safe language, like that, like the trade-off becomes very clear. Like the eventual like pivot point becomes very clear in these graphs. And I think that was one of the things that was like unintuitive to someone just sort of thinking about this from kind of first principles. And you write that the returns on investments like rewrites of the unsafe code into a memory safe language like Rust, the returns on that sort of investment diminish over time as the code gets older. And like we can go back to that. We just talked about like rewriting things like parsers or some of these higher risk things, these like applications that you're actually the thing that you're writing, not just that it's a pile of, you know, C or C++. It's the thing you're doing with it. Those things may be riskier and you still want to rewrite them in Rust so that you don't have to worry about sandboxing them or something like that. But just a pile of unsafe code. You basically write that average vuln lifetimes, 5-year-old code has a 3.4x to 7.4x lower vulnerability density than new code. You sort of kind of gestured at this in the post of why this is true. Not just that you measured it and you're able to observe it, but just the mechanisms of why. Please tell me why you think this is true.
So I think that the way I would look at it is that just the frequency that vulnerabilities are found is directly proportional to their density.
Okay.
And so if I'm doing like an Easter egg hunt, the number of Easter eggs that I'm going to find are proportional to how many that are out there in their density, right?
Okay.
And I think what you see in code is that people fix bugs when they find them.
Okay.
You know, and like whether those bugs are vulnerabilities or not, like if I go back to my Easter egg analogy, right? Like anyone who's ever like hidden Easter eggs for an Easter egg hunt and is like finding them months later, like the same thing happens in code, right? We did an analysis of kernel vulnerabilities and we found that almost half of kernel vulnerabilities are found and fixed long before they're ever discovered to actually be vulnerabilities, right?
Right.
And what's actually happening there isn't, I'm assuming, people trying to hide the fact that they're vulnerabilities. They just don't know. They found a bug and they went and they fixed that bug, right?
Yep.
And so I think that's actually the same thing that's happening here, is that as you touch code like less, mostly what's happening is you're finding and fixing the bugs over time. And that's just directly proportional to the density of bugs in that code. So the density is going down.
Okay.
I have so many thoughts. They're not good thoughts. These will all be bad thoughts, right? I want to say up front, like, you know your code. I don't know your code base. I'm an iPhone user. I have no idea how your code base works, right? But like, so I read the Alexandropoulos paper, like the open source defect density, like the decay, like the half-life of vulnerabilities in code over time thing, right? And like, it's a profound statement, right?
Yeah.
Like it's a profound observation, especially, you know, I know that memory safety inside of Android is much more complicated than can we use Rust, right? Because you also have the decision to write whole components in higher level languages anyways, right? But like that battleground between C++ and Rust it's all anybody is thinking about right now. And it's easily the most important or most talked about issue in software security right now is that frontier, right? And that observation about the half-life of vulnerabilities, if that's true, says something pretty profound about what the work looks like to kind of shift over to like the memory safe feature. I guess the first question I have is, when you're thinking about that half-life, when you're thinking about like how many vulnerabilities you expect, how resilient you expect old memory safe code to be, are you thinking about that mostly in terms of prioritizing what things to, you know, rewrite or to build in Rust first? Or are you thinking about it in terms of what memory unsafe code will we still have in the Android open source project 20 years from now?
Yeah, I think there's a couple of angles here. I think, first of all, I would actually look more at existing unsafe code as less about more like how are we going to what are we going to apply like our existing toolkit to? If we're going to spend time and effort fuzzing, like where are we going to spend that effort? And I think the other side of this is actually what's exciting about this result is it tells people that doing the inexpensive thing is actually very effective.
Yeah.
And that's what's actually really exciting about it.
Yeah.
Right. Because you have a really good system of incentives right now. It looks like my top level message from that blog post is that the incentives for AOSP are great right now, right? Like you don't have a mandate to rewrite everything. You have a sense of like how to prioritize it. And also you have things like we can get rid of sandboxes and make things easier for, we can simplify your design. It's the things you would expect to get from, what languages like Rust promise there, right? I am fixated on the computer science part of this, right? Like I buy 100% the direction you guys are going, and that you're in a good place right now. Like the early result on the experiment of doing more Rust and AOSP sounds really positive, right? So, there's a result that was published at Usenix about like the Linux kernel and OpenSSL and the half-life of vulnerabilities. And I have some just, kind of poorly informed CS kind of doubt is the wrong word, right? But questions I have, for instance, that is a CVE driven result, right? Mm-hmm. So like they are looking underneath the light post for these things, right?
Yep.
And obviously all of us have the superficial thought of, well, we've all heard about vulnerabilities that were found only 20 years after code was committed or whatever. And we know that that's not going away and all that, right? But like you have insight about your code base, right? You're not relying just on, that Usenix survey result of all those open source projects. You're looking at your own project and your own, like, it seems like you're pretty confident in those half-life numbers in your code base. And you're pretty authoritative on that. So what gives you that confidence?
So we did our own study of this, right, on our code base, and any data source that we look at seems to give us this result, which is pretty compelling. There was like another study that we looked at like fuzzing, and what it says is the cost of fuzzing actually goes up exponential if you want to scale it with the number, the number of vulnerabilities that it finds. And so it's basically kind of showing the same result, but in a different way. And so if we continue to see the same result, like any way that we look, when we look at a problem, whether it's defect rate or vulnerabilities or the cost of finding the next bug, then it's probably telling us something about like a property of software development.
Yeah.
And I think, can we say that for sure? I don't know yet, but I think like part of the reason why we wanted to publish this blog post was because like this is really what the data is pointing us towards. Mm-hmm. And we keep seeing it in different ways. And when we try to actually rely on this property, it doesn't let us down, which is like another great signal.
Yeah. So it seems like no matter which specific code base, it can be your OpenSSL, it could be a browser, it could be an OS. And if you're measuring it with CVEs, which are reported and measured in one way, or like Android's own measurement of vulns and bugs and a different reporting mechanism, like because you have like a bug bounty and things like that, even via all these different ways, they correlate with the behavior and the signal that you're seeing in terms of like how they decay over time and how mitigations like adopting memory safety and I haven't read the other Usenix study in a long time, but how the old unsafe code, quote, cures or matures over time, as it were, in terms of vulns and bugs.
Yeah.
Yeah.
I don't know. Like, it's interesting because it's a result that I simultaneously very much want to be true and kind of don't want to be true, right? Like, I don't want to be comfortable with, large amounts of memory unsafe code that we keep around just because it's kind of proven itself. It's interesting because there are other efforts, obviously, to replace memory unsafe code, right? The ISRG Proximo project is one of those, right? So I think they did like an NTP rewrite
But that's an interesting kind of different case, because that is like a full-on binary, and you can just full-on, like, it's a very well modularized and abstracted out thing. You can just do a full rewrite, and the quote, interface boundary is literally the NTP protocol, not not swapping out something that's, a core system component of Android or Chromium or even OpenSSL.
And I don't think it's applicable to the problem that Jeff, you're working on, right? But I think it's kind of a rhyming thing. And the thing that sticks out to me is like when Proximo announced the NTP thing, right? Like I have, friends that are more plugged into exploit development and vulnerability research than I am right now. And they were a lot less bullish on it than I was. Like I was much more, I wrote like a couple of Hacker News comments about like memory safety is good. There's still a live debate about whether memory safety is good on Hacker News, right? And, I wrote some like rah-rah comments about like, doing an NTP writing and Rust like makes sense to me, right? And I got pushback from people because it's like, this is not where the vulnerabilities are, right? Like one thing that these people think is happening is that like this idea that we're doing blanket rewrites of memory unsafe code in Rust or whatever, like it's kind of a huge waste of effort to them because they have a much better sense of where they're actually going to find vulnerabilities, and like this isn't where they are, which lines up with kind of the strategic thing that you're doing, right? Where it's like relying on the half-life of the code, not freaking out about older kind of quote unquote proven memory unsafe code, right? You still have other countermeasures for it and all that, right? At the same time, it's like that there have to be vulnerabilities in there somewhere.
Yeah. So the way we look at it is we're not actually trying to get to zero vulnerabilities. I know that is kind of a weird thing to say, but like maybe a better way to look at it is that if we as like, system architects are designing systems such that a single vulnerability is the end of the world, then we're really bad at doing design, right? And so like, no matter what, we have to design systems that are robust against the existence of vulnerabilities in those designs. The problem that we currently have isn't that we can't do like good like system architecture and security architecture. It's that the vulnerability density is so high, and memory safety vulnerabilities in particular are so flexible that what we see is chaining of vulnerabilities together in order to bypass good, like robust system architecture. Mm-hmm. And so I think like kind of my thought here is like, yeah, is the occasional vulnerability going to exist? Yes. And like, that's where we need to actually be applying kind of, defense in depth and like good security architecture. And that's actually the solution there. Cause we're going to have those vulnerabilities for forever, and even in like Rust code, right? Like we're going to have the occasional unsafe code issue in Rust, like,
or just logic
we
bugs.
have to be robust. Yeah.
One of the really striking things in the blog post to me was there's a graph here of the new memory unsafe code and memory safety vulnerabilities, right? And you've got like a little red baseline at 70% for like an industry norm for memory safety bugs, right? And so like things have changed, it sounds like pretty radically from 2019 to 2024. But back in 2019, you guys were still playing to win, right? Like you were one of the best, secure software teams in the world. If you just think about the amount of effort that was going into securing that platform and paying attention to software security, you're one of like probably the 4 most important targets in all of software security. So it's not like you guys were, just, phoning it in 2019. And back in 2019, all of the memory unsafe code that you had, with all of the countermeasures you had, with all of the, whatever your rules were about library safety and idioms and how you're going to, like, how you're allowed to write C++ code in this platform and sandboxing, you're still like at the norm, right? If it stayed like that, you would get the message that there's simply no way to make memory unsafe code, secure.
Mm-hmm.
Yeah, so I joined in 2014, and shortly after I joined, we had the stage fright vulnerabilities, which was kind of a huge moment. So Ben Hawks, the former head of Project Zero, wrote a really nice article about this recently, where he refers to the Android team's response to the stage fright bugs as throwing the kitchen sink at the issue, which I think is exactly what you're describing, right? Like we took an all of the above approach. And I think what we really saw with our approach was that we were able to make progress by some measures. And I'll give you like an example, which is that we saw kind of like external exploit prices start to go up quite a bit for Android. And so that would be like, maybe that had nothing to do with what we were doing. But more likely that is probably a reasonable validation that our approach was working. At the same time, the number of our memory safety issues continued to go up, not down. Which again could also be a result of maybe we were getting better at looking for them. Maybe we were incentivizing people finding them better. Who knows the reasons, right? But like it kept going up. And so part of what that caused us to do was to actually like kind of take a step back and say, this approach, while it's not like useless, do we need to look at this a different way? And so we started looking at memory safe languages as an option, right? Like, because it's kind of an obvious solution, but then of course, everyone, including ourselves, thought, okay, well, this is a solution that will, if we start now, maybe we'll have an impact in decades. Because we sit on this massive pile of legacy C and C++, and no one thinks we're going to rewrite it all.
But it's not. There's like a synergistic effect here, right? Which is like it's your big result here is like,
yes,
all of the work that you had done post stage fright didn't really seem to be moving the trend line much, right? Like it was making a difference, but like if you look at the chart, it didn't seem to change much. And it's like you have what looks like a pretty powerful synergistic effect here. You add not that much memory safe code, and all of the things that you're doing to keep the memory unsafe code safe work better.
And to put some numbers on that, from your post, the percent of vulns caused by memory safety issues went from 76% of Android vulns in 2019 to 24% in the year of our Lord 2024, well below the 70% industry norm. Like, it's still 70% for the industry of percentage of vulnerabilities to be 70% memory safety vulnerabilities, and Android is down to 24%. And that's from 2019 to 24. And it sounds like between 2015, when stage fright happened, and all the work you did to mitigate or to respond to stage fright between 2015 and 2019 still had you at 76% of vulns in Android being memory safety vulns. So
right, because, and like, this is where the insight really comes in, which is that the problem is that we're introducing them at high rates.
Mm-hmm. And this is one thing I wanted to kind of like really drill into, is that we talked a little bit about why the old code, there's the density of memory safety vulns and also like the findability. Like the density implies more findability, but also like if you're in there and touching the code and working on it, or, working around the edges of it, you're more likely to find more vulns. This is one thing that's interesting to me, is like one of the things that I seem to take away from your post is that the old code, the mold unsafe code, if we, stop touching it, we over time, if we stop touching it, it kind of shakes out the vulns that we're going to find. And if we stop modifying it and stop exposing probably things that were once safe enough, but like you change how you access the lines of code that do memory unsafe things, you all of a sudden expose a new, memory safety vulnerability that you wouldn't have exposed if you didn't touch that code in the first place. And so that seems to both indicate, one, literally stop touching that old code. And then you have to have to have an interface be up between the code that you're not touching, but you're still using, and the new code. And if that's actually what holds true, there seems to be these interacting dynamics between you aren't writing more new code and introducing new vulns, and while you're in there finding more vulns, but then you should stop modifying the old code so that you aren't exposing new vuln paths to code that was okay until you fiddled with it, or something like that. Am I making sense?
Yeah. I mean, one thing that I would say is that, this trend only happens if as bugs are found, you fix them. So you can't just not touch the code.
Yeah.
It's that you are increasingly putting code into essentially maintenance mode. And instead of, if you need to add a new feature, you don't add it into, your old C++ code. Like, okay, now I'm going to add that feature over here in Rust or Java or whatever. And that's kind of how you shift teams away from it.
Yes.
And yeah, I mean,
that's what I mean, but I didn't say it very well.
Is there something here like, if you're looking at that synergistic effect on, like, we're keeping a lot of memory unsafe code around, but then the counter vulnerabilities is dropping quickly. Is there something here about like the idea of, vulnerability scaling, not just with the amount of memory unsafe code you have, but with like the number of interfaces between memory unsafe things, like the links between modules, library call, inter-process communication, whatever it is, right? Like the number of different like individual blobs of code that are linked together somehow. And if you break that graph up, if you put more memory safe things in between memory safe code, then like if the code is more straightforward to reason about, or it's easier to confine or sandbox, or it's easier to test. Is there like a graph theoretic way of looking at this?
So I don't know. I think that's a good theory. One thing that like we're already noticing when we look at the kernel is that like certain C APIs are just like not safe to be called from Rust ever. And so what you see in the kernel is that they're actually needing to make adjustments on both sides of the language boundary, because what they want to do is they want to do, what you're supposed to do with an abstraction between C and Rust, which is that it is impossible for the Rust code to cause something unsafe to happen due to the C code. So to your point, they're having to make the C APIs safer in order to do that. And so are we seeing some of that elsewhere? I don't have an answer for you, but probably.
Okay, so like the internals, like the implementation as versus the interface, right? The implementation stays largely the same and largely memory unsafe, but the interface there has to get better just to make it work with Rust.
Exactly.
That's super interesting. That's not a thing I would have thought of. Hey, a dumb question about the vulnerability count stuff that we're working with here, right? Do these include internal? What is the level of qualification for a memory safety vulnerability counted here, right?
Yep.
Is it? It's. I assume it's not all the way to CVE. I assume like there are internal findings here.
So it probably is to CVE, and that these are through Android's vulnerability rewards program. And what that means is that we released a vulnerability. And probably what I would say is probably about, let me give you a very unscientific estimate, which is that probably about half of our vulnerabilities are internally discovered and about half are externally reported. And of course, that's going to shift all over the place.
And that figure would count both?
Yes.
If you refactored something and foreclosed, you had a bunch of vulnerabilities, but they were never discovered as vulnerabilities because you refactored them and they were like, that code was vulnerable for, this is not you don't retrospectively go back to code that was vulnerable before. I'm sure you do in a sense, right? But there's also...
It depends, because we have support windows for Android releases. So you will see, like, you can go look at the Android security bulletin, right? And you might see a vulnerability that applies to Android 14, but doesn't apply to Android 15. Yep. And we actually one of the really fun things was they switched the ultra wideband stack to a Rust stack. Woo! And within days we had released this, right? And I think 4 memory safety vulnerabilities were reported on the old one, and so we still had to report.
You should see Deirdre's face right now.
We still had to report those, but they didn't impact the latest version of Android, so they weren't, they didn't have to be patched in the latest version.
Here's the thing I'm kicking myself for not having asked earlier. What comes to mind for you as like the top 5 big ticket Rust things that are now a Android?
In Android, yeah.
It's kind of starting to show up all over the place, but I think the virtualization framework is really interesting, because if we were going to look at a big chunk of high privilege code that like applications and stuff are increasingly interacting with, that's it, right?
Yep.
The other thing The other thing is, the ultra wideband stack is a nice one to talk about. But what I think is actually really interesting is we're having less of these like big ticket, like here's the thing that we can talk about. And we're having a lot more of like, oh, this team did their new feature in Rust, which is, so there's a Rust component on a, tacked onto the side of a big chunk of C++. And that's just kind of becoming the norm.
The norm of like just any new thing is just sort of like the Rust component tacked on to existing stuff.
It's not the tacked on part that's the norm, right? It's that like new things are moving to being in Rust instead of in C++.
Okay, good. Which is like the whole the kind of like takeaway from this sort of work is like, no, really, you can get really big bang for your buck of quote kind of just doing that, which is if you have something new, just write it in the Rust or another memory safe language and make it interop with the rest of your project. And you will, in fact, get really good returns on mitigating your memory safe vulnerabilities and which is the majority of your, vulnerabilities, period. And you do not have to like have this like 10-year, 20-year plan to rewrite the world in Rust to see dividends to start paying.
Yeah. Can I tell you all, one of the reasons why we did this blog post is because, over the last few years, we kept getting these really great like results, right? And they were great, but also like they were kind of like suspiciously great.
You're like, this can't be right.
Yeah, there was a little bit of that. And what I think we kind of learned from that was we had done this study or this kind of internal analysis, and this is before that Usenix paper was even published. Huh. So like we didn't know that the kind of that distribution existed, but we looked at our own code and we looked at a couple of other code bases. And so it was quite interesting to see that like, okay, yeah, like the vulnerabilities really aren't like uniformly distributed across our code base. They really are in the code that we recently touched. So we had this idea that like, okay, this is probably going to work better than people are expecting. But then it worked even better than we were expecting. And I think the big part that we were actually missing was kind of this idea of like our older code is also getting safer.
Okay.
Like if we have a half-life of 2 years, then in 2 years, half the bugs have been shaken out of the code that, that code that was just written in C or C++. And so, 6 years later, think of the code that was written 6 years ago, right? Like it's so many bugs have been fixed and then not reintroduced because we're writing lower vulnerability density code.
Mm-hmm.
And so I think part of what happened was we had a little bit of like, I don't want to call it like a crisis, but like, what's going on here? Why is this working so well? And we had to look into this. And so the co-author on this blog post, Alex, like isn't on the Android team. He wasn't involved in like the work that we're doing on Android, but he was one of the main people who, I was kind of working with on just like investigating, like, is there an explanation for what's going on here? Yeah. So like finding that paper and also starting to find other resources that were demonstrating similar things. And then, we wrote that simulation. And like a big part of that simulation was actually like, clearly there's a mathematical model and we can simulate it. Is the simulation going to show us the same thing that we're seeing? And, imagine our relief when like the simulation, pretty much showed the same thing. And we're like, oh, thank God. Like we now have an explanation for what we're seeing and it actually matches exactly what we would expect.
Yeah. I want to like re-emphasize what like we kind of already discussed, which is that it's patching and fixing the older unsafe code over time. That's the only thing you're doing to touch it. Anything new is written in a memory safe language, and you have to like figure out your API boundary improvements or the way that the new code, the memory safe code, will interact with the existing unsafe code, which might mean improving the C boundaries on the one side and doing whatever you need to do on the Rust side or the Kotlin side as well. And then I want to talk a little bit about like all this other stuff like fuzzing and linters and sanitizers and stuff like that. But it's like you aren't doing new development in unsafe languages, and you are doing new development in safe languages is like kind of the crux, so that you keep fixing issues, but like in a maintenance mode state of the unsafe code, and you do new stuff, including improvements, new features, not just a whole new component in the safe code. And those two things together, like, make this like explosion of reduction of vulns or whatever.
So yes, but I want to be clear. Like this is like a journey, not a destination,
Sure.
right?
Yeah.
And so, you know, the idea of like, oh, you're no longer writing memory unsafe code is like, no, that's not what we're doing. We're in a transition phase.
Okay.
And like that's part of what we're trying to show in the graphs there, right? Is that it is a transition, and it's, you know, for us, it's been going on for 6 years. We still are introducing memory unsafe code, and that's probably the main reason why we're still having memory unsafety vulnerabilities, right?
But like the scale of, if you look at the scale of the decrease of memory safety vulnerabilities you have, right? Like that can't be coming just from replacing code, right? Because you haven't replaced enough code for that. Like it seems like
exactly.
The result that you have right now has to be saying that introducing some titration of memory safe code into a memory unsafe code base, even as you implement new features in C++. Like there are large existing C++ code bases that each release need new features, right? And that stuff is not being done in Rust. It's being done in C++ to get the job done, right? But despite that ongoing development, the result you have is that titration of Rust code that you have there, or whatever other switches you did there, right?
Yeah.
Like you still got a sharp drop in those vulnerabilities.
Yeah, and like, to be clear, like the drop matches exactly the number that we would expect based on the amount of memory unsafe code that's being added or modified.
Wow.
It's really an interesting result.
How much of that effect do you think comes from the introduction of memory safe code makes it easier to focus countermeasures, like, you know, sandboxing or sanitization? How much of that comes from making those things more effective? And how much of it do you think comes from just simply offsetting the amount of memory safe code there is, right?
So we think that most of it comes from offsetting. And we think that because we are also looking at other projects that aren't doing this or are doing less of it, and they aren't seeing the same result.
Yeah. But like the fact that like projects like Android and Chrome and a lot of these big projects have invested so much into fuzzing clusters, into sanitizers, into a whole bunch of like big beefy stuff, and you just start implementing most of the new stuff in memory safe languages like Java, Kotlin, and Rust. And that makes such a profound difference compared to the investment done for these other techniques. Is just like, it's kind of mind-blowing, and which is part of why like you're like, how we don't even believe what we're seeing in front of our eyes. We have to like replicate this. It's amazing. And one, there's some upfront investment of getting these new languages integrated into the project, into the tool chain, training up developers, there's like upfront cost to get that going. But it seems like especially Android has gotten kind of the flywheel going, because once you're kind of rolling, you've fronted the cost. It's not an ongoing cost of the cluster and compute and, you know, all this sort of other stuff that these other techniques bring with it. You're not paying hundreds of thousands of dollars every, you know, billing period for your fuzzing cluster.
Yeah, so like the results are really interesting, but I think the other really important part of the blog post is that it actually talks about why this scales.
Yeah.
And like really the most important reason why this scales is because it's cheap.
Yeah.
And it's cheaper than doing the other thing, right? Like a lot of these techniques actually scale incredibly poorly.
Yeah.
If for every line of, or, you know, every new function of you add in a memory unsafe language, you then have to add a fuzzer. And then now we actually need to dedicate hardware to doing that work, right? Like these things actually scale along with the amount of code that you're writing. And that's actually really, really expensive. And what you find is when, teams are under like deadline or shipping pressure, guess what gets dropped?
Yeah.
And so, if you can actually build in the safety to the code development process, then you've not only reduced the costs that you're dedicating, the additional costs, you're actually making the cost of development itself cheaper, right? Because your code ends up being safer. And I think this is actually one of like the most important parts of what we're talking about here, because when security people tend to talk about costs, they tend to talk about costs in sometimes kind of like ways that are unproductive towards like businesses that actually need to ship things.
Okay.
And so like one of the ones that like we always hear on security teams is this idea of like raising attacker costs.
Yeah.
Right. Like, oh, we've got to make the cost of exploitation more expensive. We've got to make it harder for them to find bugs. We've got to do these things, right? And like, unfortunately, the way that we tend to raise attacker costs is by raising defender costs.
Yeah.
That sounds great for job security, but it's not good for actual security, right?
And it's also bad for like your team's, how they experience working on this project and maintaining this, this code base. Like, if you're, pushing a change and you have like a million processes that are like, nope, roll this back. Nope, this doesn't pass. And then it's a lot of work to both defend the code from an attacker, but also it's a lot of work to just work on your change and just get it in and just trying to get something done. And then like one of the awesome things that, you mentioned is like just a bullet point, which is, it's not just a bullet point. It's like languages like Rust, but other memory safe languages, shift bug finding further left much earlier before you even check in the code, so that Rust changes in the Android project are rolled back at half the rate of C++ changes getting checked into the project. It means like when you have something working, passing, all the tests pass, and it's been, checked off and merged in, you're not likely to have to be like, nope, this broke. Nope, this has a vol. No, we have to back this out. And like that affects your efficiency and your velocity and also your kind of developer happiness and like productivity in general. And that it all costs money, because if your developers aren't happy, they're going to leave.
If you haven't noticed, Deirdre's trying to sell people Rust.
Like, look at all the good stuff that comes from it. Like, there's a whole bunch of good stuff. And then we haven't even talked about the efficiency of the implementation of like the QR code parser thingy that's like 1,000,000 times faster in terms of like...
It's 1,000,000 times faster because they got rid of an IPC sandbox.
Oh, well, what? Okay, and this sounds fast to me. Doesn't matter exactly why.
Yeah. So the other thing I was going to say is that like we have to get approval for like every number that we share, right? So like getting the like rollback rate was like something that we can share. But when we look at things, so let me preface this by saying measuring developer productivity is actually very challenging, right?
Oh yeah.
But like when we look at measures, we don't see measures like we can't find a measure that tells us that it's taking longer to write Rust code than it is to write C++, right? Like everything, like any metric that we can find is showing us that teams are more productive. They're going faster. They're going faster with lower defect rates.
Yeah.
And I think our director of Lars, he's the director of platform programming languages on Android. He did a talk at this about Rust Nation, but like we can't find a metric that anywhere that tells us that like using C++ is better for any type of velocity or quality. And so what I think is kind of fascinating is what that means for getting teams to use Rust is, first of all, if we can get them to switch from C++ to Rust, or when we get them to switch from C++ to Rust, teams do not want to go back to using C++.
Yeah.
Like they don't need to be like re-incentivized. They have the incentives that they want because they're able to actually ship the things that they want to, like they're able to accomplish their work with fewer barriers.
I was going to ask, right, is about the general developer experience here, right? That like, see, it sounds like the experience they're having is,, you know, once you get people to the point where they're shipping successfully on Rust, they tend to stick there.
Yeah, we don't need to like incentivize them to stay there. I would say that like, you do still need catalysts to get people to make the switch. And so, creating incentives or disincentives or whatever is still really quite useful. And, I talked about one just because we've published about it, the rule of two, right? It incentivizes teams to not add the kind of complexity and overhead of doing additional sandboxing. But there's lots of ways to both incentivize the use or to disincentivize the use of C++.
Was there anything surprising about getting Rust rolled out across the project? Like in terms of adoption and people's experiences with it?
I don't think so. So I've been on the Android team for 10 years, and it's the only team I've been on at Google. So I don't feel like I have I don't have broad experience, but like I feel like Android people are just like very practical. And so if they're told like, oh, hey, like we have a better tool for you to do your job, then people are like, okay, I'm willing to try that. And then, more often than not, they're like, yeah, this is a better tool. Let's keep doing this.
And it's generally somewhat straightforward to do like Rust and C++ in the same process, like in the same code bases, just calling across.
Yes. So Android is built on top of a mountain of C++, right? Like there's no like pure Rust processes in Android. Everything is a combination. Even things that are mostly Rust still rely on basic system libraries. And libc, libbinder, and so we did a blog post actually about interop, and I talked about the Android team being like a very practical team. I think kind of our blog post about this and our approach is actually kind of reflects this, which is that what we wanted when we looked at interop was we wanted something that was mostly convenient. And also we just kind of admitted to ourselves that occasionally teams are going to experience some inconvenience and have to handwrite a binding or something like that. And that was okay. And so that's kind of what our blog post reflected was that we thought it looked like about 90% of the cases, some like fairly standard and not that complicated tools were going to be sufficient for reasonably convenient interop between C++ and Rust. We just kind of admitted, we're like, well, we're going to keep hacking away at that remaining 10%, but also we're not going to block on that remaining 10% because the alternative is that someone who's paid to write code may be paid to write some more code, right? Like, and that's an okay thing to happen.
Yeah. And that's like the kind of 10% is like working on interop tooling like Krubit and Auto CXX. Are those some of those? Yeah. And that's kind of talking to both sides of the kind of binding layer of like, you need to do some work to make the C side interfaces a little bit better so that you can make sure that the Rust code stays safe and with correctly defined behavior when it's calling the C code sort of deal.
Yeah, what we want is that convenience, but also the safety of that convenience, right? So like BindGen is a good example of something that will just happily toss up an interface.
Lots of unsafe and other things.
May not be, it's more likely than not going to not have good safety properties.
Yeah.
And so, and we use BindGen all over the place. And then what we have is we have people who are available to review those things for teams. But yeah, like that's not the ideal state to be in. But again, I think kind of like our approach has been that we're not going to block on the ideal things. And our results are essentially that doing the okay thing is actually very effective. And so, like, what I would hope is that people aren't blocking on perfect solutions, that they're moving forward with non-perfect solutions because the non-perfect solutions turns out work pretty well.
Yeah, especially when you have results like these that literally say, not only did we not rewrite the world before we found results, not only did we just add some Rust or add some memory safe languages and not like block on perfect solutions of binding generators or anything like that are perfectly memory safe and have defined behavior or whatever. But we kept writing C and C++ in some areas of our project, and we still had a major reduction in memory unsafety vulnerabilities over 5 years. So like having the extremely material results of this, like, don't let the perfect be the enemy of the good, of like, just get started. If you just get started, you will have like crazy ROI on your investment. And the ROI scales. It's not even like, it's like going to be linear indefinitely, but better than the thing you did before. It's like you do a little bit of ROI and like it's kind of plateaued in terms of the investment. It just keeps on growing.
Yeah. It's funny, right? Because, I think this isn't just security people, but software people in general really like to be, kind of pedantic. So yeah. You all work in cryptography, right? And in cryptography, that's a necessity.
We have to be pedantic. Not all software has to be pedantic.
Yeah.
The word you're looking for is rigorous.
Yes. Thank you. Thank you. Much better word. But yeah, I what I would say is that like when we show these results to teams that are wondering like what they should do, like they really do kind of change. Like a couple of examples are like teams who are like, well, it doesn't matter if we use Rust for this thing because this other thing's in C++, and therefore all bets are off. Toss everything out the window. Might as well C++ for eternity. And then the other one is, it's like you're almost giving teams permission to be like, no, the stuff that you like, your work, your previous work, your team's investments, like, those are still good. You get to keep using those. Like, we're not telling you to throw out everything that you've done. And so that I think there's also kind of like a sense of like ownership that people want to retain in the work that they've done and the code that they've written. And it just ends up being very convenient that the result says that that's probably something that you should do. And one of the things that we had originally put in the blog post was kind of a stronger statement about like, hey, like even in memory unsafe code bases, about a third of your bugs are non-memory safety. So, if you have code that say you could calculate that, 2/3 of the bugs have already been fixed in this, or more than 2/3, and you go and rewrite that, odds are you're going to reintroduce all of the non-memory safety bugs, or, you just have high potential of doing those things, right? And so it just like, maybe we shouldn't be doing that at all. And
like, basically, this is evidence that you really don't have to.
Yeah.
Like you get extreme bang for your buck, and it makes all those things a lot easier to get started.
Yeah, I mean, look, the blog post undersells it, right? I think it's a pretty huge case study that you've got here, right? Like this is, like I said, this is one of the more important security target code bases in the world. And yeah, I mean, just in terms of the ROI you guys have gotten on, it looks like kind of a practicable amount of, introducing Rust code. It looks like a pretty big win so far. So, yeah, I'm psyched to see how this plays out moving forward. But yeah, this is a lot more interesting than it looks like on the tin. Like, yeah, we rewrote some stuff in Rust. That's not the story here. So, yeah, super interesting stuff. Thank you.
Thank you, Jeff. Do you have anything else that we didn't touch on that you want to send us off with?
I feel like
you don't have to.
I feel like we actually discussed most of what I wanted to talk about. I'm glad we got to talk about the like kind of shifting away from like an attacker-based mindset. I think that's one of kind of another like novel thing to talk about to security folks, especially on this topic, because it's so just kind of like ingrained in everyone that like we look at what attackers do and our primary goal is to like frustrate attackers.
Yeah, it's interesting, right? It's like there's like like if you talk to like lawyers, right? Like you have like a mental model of a lawyer as somebody who goes into court, but most lawyers aren't in court ever, right? There are litigators, and then there are people who do like contracts and review and strategy and all that stuff, right? And here you've got like, this is like, I don't know this is going in, right? But like here you've got like this thing where you've got like, you have a software engineering answer to this problem. Like you're looking at as a software engineering problem, not as an adversarial process against attackers, right? Like it's, there is that process happening at the same time, but like you also want the nuts and bolts of things. You want to be situated well so that like if you ever do come into contact with, attackers, right? Like you're in a much better position. So yeah, I mean, I'm also a sucker for software engineering stories. And yeah, this is
Yeah.
It's like, it's pure software engineering. It's awesome.
Yeah. So, I talked about like raising the cost for attackers and how we do that with like exploit mitigations, but there's even like fuzzing, right? Where it's like, it's not even like that this is a good tool for defense. It's almost more like we're going to do the attacker thing first because that raises their costs, and not because it's actually a good thing for defenders to use, right? Like fuzzing actually is a little bit problematic for defenders because obviously attackers only need to find a couple of bugs and defenders need to find more of the bugs than the attackers. But yeah, to your point about it, like being a software where answer is that's what I think is actually really exciting about it. And why it actually kind of works in defenders' favors, because it's like, we're just like ignoring the attacker, right? We're saying like, this actually drives down our costs. And it drives down our costs by just improving the software quality. And then of course, it almost ends up being a side effect that it actually drives up attacker costs. So it's, by trying to make our own lives easier, we've made attacker lives more difficult. And like it's just kind of an interesting result by, instead of focusing on attacker strengths and trying to undermine attacker strengths, we actually said, no, like defenders have their strengths, and their strengths involve things like owning the developer environment. And so instead we're going to focus on our strengths. And it's at least an interesting area where that works. And I will say, like, it doesn't just work in memory safety. It actually works in other areas. Like, we mentioned like cross-site scripting, or there's like SQL injection or things like that, where we've like applied the same technique and seen like similar results. And I think what's kind of exciting about memory safety is this was the one where it was like, oh, sure, that works in those little areas, but will it actually work in kind of like the industry's Achilles heel? And I think so far it looks promising.
Yeah. And like, this is sort of like the memory safety part of these languages, but like the same can be said about some of the other nice features of languages like Rust, which is like strong, cost-free typing, and like a whole bunch of other stuff that just making correct code a lot easier and just ready to go. And the tooling is there for a developer to just do quote the right thing or do a good thing very easily and very, it's not like dragging yourself over a glass to do the right thing. The language and the tooling make it very easy and helpful to just do the right thing, and it's fast and it's efficient, and you just get to ship good code much easier, and it mitigates other classes of vulnerabilities besides memory safety, and it's the same sort of effect. And it just makes the software better, which happens to make it more secure and the attacker costs low. And it makes it lower cost to the business who's actually doing the project or anything like that. So you can sell your CISOs or whoever on like, this is a good idea because it'll save you business money and money and costs for the attacker too.
Yeah.
Jeff, thank you so much. This is awesome. Thank you so much for letting us pick your brain with lots of annoying questions.
Yeah, thanks for having me.
Totally. Security, cryptography, whatever is a side project from Deirdre Connolly, Thomas Tatchak, and David Adrian. Our editor is Nettie Smith. You can find the podcast online at SCWPod and the hosts online at Durham Russellum, at TKBF, and at David C. Adrian. You can buy merch online at merch.securitycryptography.whatever.com. If you like the pod, you can give us a 5-star review wherever you get your podcasts. Thank you for listening.